Welcome to Finite Element Tutorials. We'll be studying the behavior of launch vehicles when they're subjected to ground winds when the launch vehicle is on the pad. And we're going to be studying a number of problems related to that: seismic analysis, wind analysis, static analysis, and model dynamics. For that, I'm going to pass it to Lifu Wang, who will guide us through this exciting tutorial.
Hello everyone, welcome to another Fun Element tutorial about modeling of a launch vehicle. And here's a problem statement. You already see it in your project Word file. So I've converted all the units into inches and palms, inches, and seconds, because some of the units is meter per seconds. And here's the result. So this is a model. This is a symmetric axis, and we are going to use 3D shell for modeling everything. And the thickness for different part is generally split it into 5 parts. Part A is the tip. Part B is the side. Part C is this transaction area. Part D is a tank. Part D and E are all tank filling with fuel or something. And the thickness for different parts is different. ABC has a thickness of 0.1 inches, while D and E has a thickness of 0.6 and 1 inches, which is thicker because it's under pressure, internal pressure of 400 psi. That's why it needs to be thicker. And then we're just assuming the material for the launch vehicle is stainless steel. The Young's modulus is 30 mega psi and Poisson's ratio 0.2. And the density here I want to mention is 0.285 pounds per inches cube. But in Abaqus, the density units we're going to use is the LBF second square over inches fourth. So to convert this to this unit, we need to divide by the G, which is 386. And this is the final number for that enters into the that enters into the Abaqus. And also the velocity here is a non-uniform distribution. So this project is more like a combination of all we learned for the previous projects. It has nonlinear distributed load. It has model analysis. Plus, we're going to learn how to use apply the seismic analysis today. And the velocity after unit conversion, you should have this value, and the pressure is just 0.5 CD, which assume it's to be 1 and times rho times u squared, which is this number. Double check these numbers because I may make some mistakes during the conversion. And also this 2 plus give you the k, which is the exponential number, and the initial velocity, which is this number. The boundary condition we are going to apply with there are 4 pins at the base of the rocket, but we are going to make it simple. So it's going to be 4 pin nodes at the 4 corner. That's the only boundary condition we have. So we're going to make some changes to the homework. We're going to delete the problem question 5. So you only need to do the first 4 problems. And probably this is going to be split into 3 different videos. And the first one, I'm just showing you how to do the natural frequency with preload. And now plus how do you create the model, which is this step is the same as previous projects. And the second one, we're going to compare a static analysis with pressure increase, with a wind pressure increase by 35%, and which is this value. So you can see originally the incoming wind has a value of this, and now is this value as the amplitude. And then we're going to compare that with the model dynamics with 0.5 seconds of impulse, same value of static and load, and see how does the result different between these two cases. And the third video is going to be seismic analysis for the input file given to you as a horizontal amplitude and a vertical amplitude. And we're going to use Abaqus GUI to solve the seismic analysis problem.
Excuse me, Lifu. Let's have other students in the course demonstrate how they develop the geometry. They want us to feature the approach that they use to get the geometry done. And after they illustrate their approach, I'll then transfer it over to you. Thank you, Lifa, for your patience. Let's check it out and see how that's done.
So as we know before in Abaqus, we go in and set our working directory. And then we hit new part, and we're going to go and, like Rafe said, we're going to do the 3D model. So 3D, deformable, solid, and then hit revolution. And here we can just do 50. And once we are in the sketch, we can do hit the connecting lines. And then we start with the first coordinate, so 1.67, 0, 1.67, 3, 1.67, 45.7, 2.74, 49.4, 2.74, 79.8, and 0.19, sorry, 914, 4, 83.8. And this is what it looks like. So then hit done. Then we can, so since each of these sections has a different thickness, then we need to use construction lines to split them. So pick construction lines, go here, create a construction line here, and then create another one here. And then one more here. So now these should be split. I think I need to do. So now this is split. I had to select this split line. Now we need to offset to create the offset. So I can start at the top. And these first three sections all have the same offset. So if I just select all of these, hit done, and it's 0.00254.
Yep.
And then hit OK. And then this next section is 0.6. So go ahead and hit done, and it's 0.015.
24.
24. Thank you. And
Yeah.
okay. And then the last part is 0.02454. No, 24.
So it's 0.02.
4, right? And that's done. Then we need to connect these sides. So go here and connect these two. And then I'll need to go in the middle here in the next section. That's the end of section E. Connect this one and this one.
Shahad, did you want to tell everyone why we're not connecting it all the way through to, if you want to zoom in?
Yeah,
quick.
actually, you want to explain that?
Yeah, so we're not going to connect all the way to the other end because otherwise it's not going to be able to rotate. We kind of learned that through trial and error while we were, working on this, and it makes sense because otherwise you'll be breaking the sections into two separate ones, and it won't be able to rotate that part.
Exactly. And then you'll see the next part has the same problem. So right here, I'll just need to connect it from this end to this end. And then the last part at the top. Okay, so this is all we need to do. This is our final model. I can go ahead and hit done. Then select a construction line at the center line. So hit this blue. Then I can do 180, hit OK. And here's our model.
Thank you so much for guiding us through that geometry generation. I'll pass it to Lifu Wang, who will start from scratch again and show us his approach.
First, set your working directory to the folder you want, and make sure that you have these two files, input file in your folder. And then now let's create a model. So in the parts, create the launch vehicle. And so it should be a 3D deformable shell. And let's do 6,000 for this revolution. Because if you see the original file is 33,000. And this should be double the size. So let's do 6,000. Enter the important point. Already give you the coordinates of these points. Originally it's in feet, now it's in inches. You can double check this number if they're correct or not. So 0, 0, 66, 0, 66, 120, 0, 120, and 66, 1800, 0, 1800, 108, 1944, 0, 1944. And then 108, 3144, 0, 3144, 36, 3300, 0, 3300. So now we use line to connect them together. We're going to have 4 ribs here to support the geometry. So we need to connect this line. So let's connect the outer shell first. Now we connect the ribs. This is the first ribs. This is the second ribs. Third one. And the last one. And we're going to rotate 360 degrees, so we don't need to apply boundary condition. But this is the geometry you have. Now we assign property. Create property stainless steel. Density is 407487. 407487. And then elasticity, Young's modulus 30 megapascal, 30 megapsi, and then 0.265. Since we're going to have 3 different thickness and the thickness is assigned to the section, so that means we need to have 3 different sections. Now we create sections. Section 1, shell, homogeneous, and the thickness, the first one should be 0.1 inches. Section 2, homogeneous, and the thickness is 0.6 inches. Section 3, homogeneous, the value should be 1 inches. And now you can see that all parts that is not under pressure will have 0.1 inches. So now we assign section. And now we're going to create set here. So it's easier for you to check. For last project, I found out a lot of students have this question, like Abaqus report something has an arrow peak or arrow selection, but you don't know what surface it is. Now, from now on, we are going to create sets and surface and name it in a unique name. So later when Abaqus have some report for arrows, you can went back and check what the arrow is. So let's call it thickness 0.1. Abaqus cannot use dots for naming, so use P as dot. Sorry, I haven't selected that. So thickness 0.1 and select everything here, everything about this cross section. To select that more accurately in your view, choose parallel so it won't have the perspection. Now let's go to XY view and zoom in a little bit and select all of that. Everything above this length. So done. Use section 1. Double check your section 1 should be 0.1 in thickness. Now select the same thing. Now we're going to hide it. And for the remember that this rib should be included for the second part. Since this rib should be included for the second section, since this rib is also under compression, under pressure. So now we're going to create the section 2, which is everything above this section. So call it thickness 0.6. So choose section 2 for that. Now we're going to hide this part. And whatever left will have 1. We'll have a section of 1. So it's thickness 1. Have a thickness of 1. So now you should have everything in green. That means the material is assigned correctly. Assembly. Create assembling instant independent. And step. I'm going to only show you how to do the preload and get the natural frequency. I think in your original problem, you're asked to compare the natural frequency with and without preload. So here, step. With preload, we need to apply the static analysis first. Call it preload. If it is without preload, you can disable this step. So if you have preload, you have to turn on the nonlinear geometry. And we can start from 0.1 and leave everything default. Now we create the frequency step, which give you the natural frequency. call it frequency extraction. And we don't need to use damping operator here. And our maximum frequency is 30, but I think there are too many modes here. So to limit the number of modes you have, let's put 200 modes here. So it has two limitations. The maximum frequency should be smaller than 30, and the total number of modes should be smaller than 200. And I'll show you like why there's so many modes here. So once it's done, if you want to make your results smaller, here you can change a little bit. Originally, it has a lot of things. So actually, we only need the displacement here and the stress. Also here, we only need displacement, definitely. And mesh, in your mesh control, select everything, and then you sweep here. So now we are going to mesh different part differently. For, oh, sorry, I forgot to do one thing, because you can see here, we only have one node at the bottom. But later, when we apply boundary condition, we are going to apply at 4 different nodes here. So go back to assembly here. And we are going to partition this into 4 different pieces, this instance into 4 different pieces. To do it, let's create datum plane first. So this should be your XY plane. Choose XY plane, we don't need offset. And then we need another YZ plane. So YZ plane. So you can see your 2 datum plane here. Now long click this one and select the third one, partition faces using datum plane. Select everything, select the first datum plane, enter, select everything, select the second datum plane, enter. Don't select the wrong datum plane. Make sure that after this step, you should have 4 nodes here. This one, 4 part, this part, this part, this part, and this part. Now let's go back to the mesh. Oh, actually, we should follow this one. So let's do load first. So create boundary condition. I prefer create boundary condition first. So the boundary condition in the initial is ping. Choose the first one, and then select the 4 node we have, hold shift. Make sure your selection is correct. Call it and call it ping. Create the set and use the ping here. And now we're going to apply the load. Go back to XY view. So we hide the upper half first. So we are going to have 3 different pressure. The first pressure is going to be applied on this side shell and this side shell with 400 psi. The second pressure is applied on this top shell, and the third one is applied on the bottom shell. So to do that, let's create the first one first. So this pressure should be applied at the preload. Call it pressure 1. Create surface, call it side shell. Here, hold shift to select every side shell here. Make sure that, see, my selection is all the side shell here, and here don't touch any boundary. Don't touch any boundary for the shell. So we're going to apply it in the inner surface, so it's purple, it's not brown. And 400 in magnitude. Now again, select this 2 shell and then hide it. Whatever left is what we are going to apply pressure on. And the middle one actually has a pressure at both top and bottom. It won't affect a lot for the geometry. So we are not going to apply pressure on that. So apply pressure too. And this time it should be the top surface. Call it top shell. And it should be the brown. 400. Now look at the bottom. We're going to apply pressure 3 to all the bottom surface. Call it bottom shell. And use purple for that. It's the purple 400. Now get back everything. Make sure that your load is correct. Now we can go to the mesh part. So mesh control, select everything and use swap for that. And then assign node, assign seed for different part. For your part 8, only the side, let's assign, let's use by number and probably let's do 8 here. So then it's this one. And let's do 20 here. So use this tool first and select this edge. And then 8 here. Here we're going to select this one and 30 here. Finally, finally select the last one and do 8 here. This is and we need to assign load to the side lengths. So basically you can do in this way. Let's do XZ direction. So you will have or you can directly assign globally. So other than the line we just selected, everything will be this globally. Or actually, since we want number, let's still use this assign line. So select this 4 line and do probably 8 or actually 10. Select this. Select this. Yeah. So make sure that everything is 10. And then is this 10? Yeah. So now we can mesh. They should look like this if you do it correctly. The top should look like this. The bottom should also look like this. It's equally split into 10 pieces. And well, vertically speaking, it's like this. Finally, job. Now let's create the preload frequency extraction. can submit. It may take 4 to 5 minutes to finish this step. It doesn't take long to finish. You can see the at first we have an arrow because 0.1 second is not enough for converge. So it automatically turned down to 0.025 seconds. But it's fine. The first step is pretty fast. And the second step takes some time, probably like around a minute or so. Can roughly see the step time for your nonlinear nonlinear loading is increasing, which means your solution is converging here. Now we can look at the results. So let's go back to the step 11. This is the step that after the preload. You can check your stress, von Mises stress, and displacement or something. I think the maximum displacement is at the top head. We can double check that. So select everything up to here. Remove it. Yes, you can see the stress is, the maximum stress is mainly here on this ribs. And then let's go back to XY. And now start from here is the Modeshape analysis. You can see the natural frequencies here. These are some buckling mode. Although it looks pretty crazy shape, but this is after normalized. So you will see it's very large. It's increased by 204 times of the actual displacement. That's why it looks pretty crazy here. But it doesn't matter. This is buckling mode. And this is the mode that we need to pay attention to. Let's go to XY. This is a bending mode. You can see that it bangs to the positive X direction. And the natural frequency for that is 0.7 hertz. And this is a second bending mode. And from now, it's still some buckling mode. This is buckling for the head, for the tip, because we're always using shell elements, so it will have buckles. There's also one type of buckling mode. And now this is your secondary bending mode. This is what we need to pay attention to. It's mode number 12, and the frequency is like around 3. And buckling mode doesn't make any difference. And then you can see that 200 modes, we captured only 2, like the maximum frequency is around 20 or something, 22 or something. So it haven't even reached 30. So because we have so many buckling modes here, it also depends on your mesh size. And so it's up to you. If you want to have a better result, probably you need to increase the number of modes to like 300 or something. So that's it for the model analysis with preload. And always remember that the one that affects our result later is the bending mode, which is, for example, this one and this one, and the very beginning, first one. Yeah. Because later we're going to apply the wing pressure to it. That's for the first video.